Hello, this is T Chapman 500, and today I thought I would do a video where I rebuild my original 8-bit CPU. Yeah, the one that I mentioned that broke in an earlier video that I posted last year. So I'm starting off with some of the registers, namely the accumulator and output registers. And then I'm going to be doing a few other things like the arithmetic logic unit. Right now this is the accumulator, and I'm working on adding a thing to the appearance of the circuit that allows us to see the data that's in the accumulator. It's also the case that I'm putting in the general purpose registers. So I'm using just a RAM block for this, since this CPU doesn't have to worry about reading from two addresses at once, or two registers at once. So using the generic RAM component is fine. If I wanted to read from two registers at once, I'd have to do something else because the Logisim doesn't allow that for the RAM component. So this is the output register, and again showing the data that's in the register. And after this comes a slightly more complex circuit, mainly the arithmetic logic unit. But first, I'm actually building the adder for the arithmetic logic unit, as well as a few signal flags for controlling it. The XOR gates are to enable subtraction, and I use a bit extender, which is basically just copying a single wire over to all 8 inputs of the XOR gate in the middle. And then there's also the output that I need to put in, or the output enable that I need to put in, that will make sure that it doesn't short out anything else on the circuit. So the instruction set will allow the CPU to add with a carry or without a carry, so that's 2 instructions there, and then subtract. There is no subtract with carry or subtract with borrow in this CPU. So the adder can do a subtract with borrow, but the instruction set does not have that capability. And you might have noticed that I had made a mistake with labeling the component. I originally labeled it as the ALU, which means arithmetic logic unit, when I actually made it the adder component. So I fixed that. This component right here is going to be the incrementing and decrementing device, which, as you can see, is a bit simpler. It has signals to, well, it has the read enable signal, but it also has only one other signal to switch from incrementing a number to decrementing a number. Increment means increase by 1, decrement means decrease by 1. And I just tie the decrement and subtract signals together because there's no point in having multiple signals when there's only going to be one of those signals active at a time. Or rather, one component active at a time, so we can share the signals and not get contradictory results randomly. So this is the negator. It's even simpler as we don't have to change signals. And it's also the case that for incrementing, decrementing, and negation, you don't need to load the accumulator. The accumulator is going on the B input of the register. So, at least for some instructions, and the not instruction also doesn't need you to load the accumulator. So, for some instructions, you don't need to bother with loading the accumulator. But with other instructions, you move the register that you want to be on the B input to the accumulator. Then the operand for the instruction goes to the A input. So right now I'm wiring up some of the flags. The carry flag goes to the control unit, and it will also go to the carry in, like there, to the adder. And there's not going to be a dedicated comparator. Alright. There's not going to be a dedicated compare component because the comparison is merely a subtract operation where the output is simply ignored. We just want the 0 and carry flag. Now this is the shifting operations. We have a shift left and 2 shift right operations. The shift right has a signed and unsigned variant. And the reason for that is so that we can copy the highestmost bit to the right, however many bits we're shifting, which is pretty useful for creating bit masks. However, it's also used for other things it's used to preserve the sign of a number. So shifting right is equivalent to dividing by 2. So if we do a sign shift right, that's essentially, say, -10 divided by a power of 2. I misspoke. Shifting right is dividing by a power of 2. Shifting left is multiplying by a power of 2. And on this CPU, all multiplication and division will be done with this shifter. And there's not going to be a multiply or divide instruction. You will have to manually implement multiplication and division using shifting, addition, subtraction, and negation. There's also not going to be a signed compare instruction either. It's going to be unsigned, and you're going to have to manually implement in software a way to determine if a number is signed or unsigned. Now this is for the standard AND, OR, NOT, and XOR operations for a CPU. And I'm controlling those 4 operations with simply 2 signal flags. So AND and NOT are on group A, OR and XOR are on group B, and then we have AND and OR on set A, and NOT and XOR on set B. So it's a bit of a hierarchy for, or inverse hierarchy for the instructions. Now here I'm trying to set the positions of all these signals and whatnot so that it makes some sense when viewed from the outside. And yeah, it took me a little while to determine how the components should be wired and positioned relative to each other. And the idea is, well, the arithmetic logic unit outputs to the output register, which then goes to the bus, and we can have multiple things going to the bus at the same time. And since the arithmetic logic unit is done, I'm just cleaning up a few of the signals, and in a few minutes I'm going to try to put in the main RAM as well as the interrupt handler. So I'm going to be adding a few more circuits to address the main RAM. And then I'm going to put in the interrupt handler. Now, I've been trying to make it so that we don't get a four-way intersection of a specific signal. So a signal does not branch left, right, and forward at the same point. That's because Logisim has this thing about accidentally breaking signal connections when you have a cross formation on one of your signals. So this is the address register, and it's basically going to serve as the template for the other address registers. This will go to the address of the RAM and to the peripherals, like the GPIO pins, which will be able to serve as interrupt pins. And you'll basically communicate with the CPU from those GPIO pins, which are mapped to specific addresses. So the address register is going to store an address, a pointer that is loaded from RAM or modified from the data, and it can be loaded either from the address bus, actually only from the address bus, and it can be loaded to the address bus. Or, hold on. Yeah, it can output to either the address bus or the data bus. And I decided to do split register because that's a bit simpler than trying to do some stuff with a full 16-bit register and manipulating the wires and whatnot to defeat the purpose of the register's design. So, like the rest of the things, I am showing the register's state, and this part is actually going to be quite a bit more complex than I originally anticipated, so it's not going to get done in this video. So the final component that I'm about to add is going to be the interrupt lookup table. So there are going to be a maximum of 256 interrupts. Each one will have an address that points to the function that handles that specific interrupt. And I'm also labeling all of the RAM components, which are being used to save on processing power on the computer that is running the simulation. Anyways, hope you enjoyed the video. Please leave a like if you did. Don't forget to subscribe. If you want to support this channel, you can do so on Patreon, PayPal, or Subscribestar. Other links and all those links are in the description. This is T Chapman 500 signing off.